You set a memory limit on a container, 256 megabytes, and the container tries to allocate 300. So what happens? It gets killed immediately. Exit code 137, see kill. But here's the question no one asks. Who killed it? Docker, Kubernetes, or Containerd? But the answer is none of them. The Linux kernel killed it, specifically a subsystem called control groups. So cgroups enforced the limit you set, noticed a violation, and triggered the OOM killer. And every resource limit you have ever set, CPU throttling, memory caps, or I/O bandwidth, it all goes through cgroups. And if you don't understand how cgroups actually work at the kernel level, you're debugging in the dark. Today we are going deep. We are going to look at two architectures, cgroup v1 and v2, understand why v2 exists, and learn how Kubernetes translates your pod specs into kernel-level resource controls. So, let's start at the bottom. Control groups entered the Linux kernel in 2007. The problem they solved was simple. How do you limit what a group of processes can use without modifying every application? Before cgroups, they had individual process limits, U-limit. Nice values, but no way to say these 50 processes as a group can use no more than 2 CPU cores and 4 GB of RAM. Cgroups solve this by creating a pseudo-file system. You write numbers to files, the kernel reads those files and enforces limits. But there was a problem with cgroup v1, a design problem that took 10 years to fix. v1 allowed every resource controller, CPU, memory, disk I/O, to have its own independent hierarchy. The same process could be in one location in the CPU tree, a different location in the memory tree, and yet another in the I/O tree. This created management chaos. Who owns the cgroup? How do you delegate control? What happens when you want to migrate a process? Do you move it in all hierarchies or just one? This is why cgroup v2 exists. v2, one hierarchy. All controllers attached to the same tree, a process can only be in one place. Clean, but fundamentally different. And we need to understand both. v1 is still widespread, older kernels, legacy systems, and v2 is the future. So Kubernetes defaults to it, and all modern distributions. And here is what matters for production. Kubernetes quality of services classes. It's guaranteed, burstable, and best effort. And all these classes map directly to cgroup configurations. And if you don't understand cgroups, so you can understand why your pod was wicked. So let's build that understanding. A cgroup is a kernel data structure. When you create a directory in CSFS cgroup, you are not creating a file system directory. You are asking the kernel to allocate a struct cgroup and then expose it as a directory. Every cgroup has a parent, except root. This creates a tree, and resources flow down the tree. Parents subdivide their allocation to children. Now the kernel exposes controllers, and each controller manages one resource type. Can be CPU, memory, I/O, paths, and CPU set. Each controller has control files, you write to them, and stat files, you read from them. Kernel enforcement happens at allocation time. Let's trace a memory allocation. First, process calls malloc, for example 100 megabytes, Then kernel handles page fault, then calls memcgroup charge and asks, does the cgroup have room? It checks, does current memory plus 100 megabytes fits in limits. And if yes, it's allocate memory. If no, try reclamation and then OOM. The process blocks until the kernel decides, allocate or kill. And this is why memory pressure causes stalls before OOM kills. Now that we understand the basics, let's see why the architecture changed. In cgroup v1, every controller is a separate mount point. Each is an independent tree. So let's create a v1 cgroup. Notice that we wrote to cgroup prods twice, and that's the problem. The same PID can be in different positions. And we have questions like who managed this process and what's its effective limit when controllers conflict. Kernel handles this, but management tools struggle. Systemd, Docker, Kubernetes, they all have to maintain per controller state. It's complex and error prone. In version 2 we have one tree, and there is key architectural rules. Rule 1 is unified hierarchy. All controllers attached to the same tree. A process is in one location across all controllers. Rule 2. No internal processes. Processes can only exist in leaf nodes. Interior nodes are for delegation and control. When we attempt to write PID to interior node, we got rejected. So, because v2 enforces clear separation, interior nodes manage resources, leaves contain processes. Next rule is explicit controller delegation. Controllers must be explicitly enabled per subtree via cgroup subtree control. So the plus and minus syntax enables or disables. This is delegation. Root says my children can control CPU and memory. The child can then say my children can control CPU but not memory. In v1, any cgroup could use any controller if the hierarchy existed. No security boundary. In v2, unprivileged users can be given a cgroup subtree with specific controllers, and it enables rootless containers safely. This unified hierarchy is why Kubernetes prefers v2, simpler, safer, and more predictable. And before we dive into the mechanisms, let's establish what CPU control actually means. So, when your application runs, for example, processing an HTTP request, parsing JSON, running a database query, it needs CPU time. And CPU time is literally the processor executing your code's instructions. If the process gets CPU time immediately when it needs it, the request completes in 20 milliseconds. But what if CPU time is limited or delayed? And this is the core problem. When cgroups limit CPU, your process doesn't get slower CPUs, it gets less access to the CPU. It must wait, and waiting equals latency. The CPU controller integrates with Linux Completely Fair Scheduler, CFS. Two mechanisms. First is proportional shares. It is CPU.shares in v1 and CPU weight in v2. There are two cgroups competing for CPU, and shares are not CPU core allocations, they are weights in a lottery. Though contention, everyone can burst to 100%. Second mechanism is hard limits. It is cpu.cfs quota US and cpu.cfs period US in V1 and just cpu.max in V2. So, but what happens from the application's perspective? Let's say your API server receives a request that needs 18 milliseconds of CPU time to process, but you have a 50% CPU limit, so 50 milliseconds per 100 milliseconds period. This is why throttling causes latency. The process is runnable. It has work to do, and the CPU cores might even be idle, but the kernel won't let it run because it exceeded its quota. The request waits, and your user sees latency. So on the kernel level, the CFS scheduler calls function update cur on every tick, and it checks runtime remaining for this process. And if there is no runtime remaining, it uses function throttle CFS RQ to move this process to throttled queue, and then throttled processes cannot run until unthrottle CFS RQ function is called at period boundary. And this is why CPU limits are dangerous for latency-sensitive workloads. A web request might need 10 milliseconds of CPU time spread across 50 milliseconds of wall clock time. So if it hits CPU quota, it waits, and P99 latency spikes even though average CPU usage looks low. So for latency-sensitive workloads, for example, API servers or databases, you should use CPU wait and not CPU max. CPU max throttling causes tail latency spikes, and processes wait even when CPU are idle. For batch or background jobs, use CPU max to prevent runaway consumption. Memory controller has two key limits. In V1 we have memory.limit in bytes, its hard limit just OOM kill on exit, and we have memory.soft limit in bytes, its soft limit reclaim under pressure. And we have the same in V2, its memory.max, its hard limit just OOM kill, and we have memory.high, its soft limit, it just throttle allocations and no kill. So when process allocates memory, there is malloc function, then page fault, then mem cgroup charge checks if current plus allocation lower or equal limit, if under limit allocate immediately, if over limit try reclamation. And in the case if reclamation fails, the process gets killed by OOM kill process. And this is synchronous and blocking. The allocating process waits while the kernel tries reclaim, and this causes memory pressure, performance degradation before OOM. But which process gets killed? Kernel calculates OOM score for each process in the cgroup. Higher score means more likely to be killed, and root processes have penalty, less likely. And also, there is OOM score adjustment. It can be set per process, from -1000 to +1000. Kubernetes sets OOM score adjustment based on quality service class. In this case, best effort kill first, burstable proportional to memory request, and guaranteed kill last. So, this is one of V2's killer features, pressure stall information, PSI. Traditional monitoring is reactive. Just OOM happened or process was throttled, and you find out after damage is done. And PSI is predictive. It tells you how much time processes spend waiting for resources before hitting limits. And PSI is available for monitoring, not for automatic eviction. PSI metrics are exposed by the kernel and available in Kubernetes via cAdvisor metrics. However, kubelet does not use PSI for automatic eviction decisions. It uses traditional metrics like memory.available, and PSI can be used by custom controllers. Each PSI metric has 3 files, and content format is like this. Sum means at least one process was stalled, and others may still run, and full means all processes were stalled, complete blockage. AVG10 means average pressure over last 10 seconds, it means short-term spike. AVG60, average over 60 seconds, medium-term trend, and AVG300, it's average over 5 minutes, long-term baseline. And PSI is tracked by the scheduler and memory management code. Every time a process is runnable but not running, for example by CPU pressure, or blocking on memory reclaim, or waiting for I/O, the kernel accumulates stall time. As I said before, PSI metrics are available in Kubernetes for monitoring via cAdvisor, but kubelet does not use PSI for eviction decisions. It not works out of the box. And eviction is based on memory.available and not memory.pressure. Custom controllers can be built to use PSI for proactive decisions, but this requires additional tooling beyond kubelet. Let's see CPU throttling in action. We'll create a cgroup, set a 50% CPU limit, and watch the kernel enforce it. First, we need to verify that we're on cgroup v2. Good. Single mount point, cgroup2 type, we're on v2. Then we'll create a slice for our demo, set CPU quota and memory max, and then systemd run creates a transient service. And it automatically creates a cgroup, enables CPU and memory controllers, and sets limits. So, let's find the cgroup path. Okay, and navigate to cgroup directory. Now let's check CPU limit by cat cpu.max. And we have format quota period in microseconds. 50,000 microseconds quota out of 100,000 period. And it equals 50% of one CPU core. And now let's start a CPU intensive workload in the same cgroup. We will get PID of our sleep process and then run stress-ng in the same cgroup by using systemd run with same scope. And let's watch CPU usage in real time. Even though stress-ng is CPU intensive, it's kept at 50%. And let's see the throttling statistics. We have NR periods, it is how many quota periods have elapsed. NR throttled is how many periods we hit the quota limit, it's almost every period, and throttled USAC, it's total time spent throttled. But what's happening in the kernel? Every 100 milliseconds equals one period, the CFS scheduler checks runtime remaining. Our CPU intensive process uses up its 50 milliseconds quota in the first 50 milliseconds of each period, and then gets throttled. The process is throttled in every period because it's always trying to use 100% CPU, but only gets 50%. It runs for 50 milliseconds, then waits for 50 milliseconds, repeatedly. Process cannot run until next period, even if CPUs are idle. And this is expected behavior. Notice that NR throttled is almost equal to NR periods. This proves throttling is working correctly. The process exhausts its quota in every single period. The key metric is throttled usage, which shows about 50% of total time was spent waiting. And this is why CPU limits cause latency. If your API server is throttled, requests queue up, even though the node has free CPU. This is the trade-off: strict limit enforcement at the cost of potential idle resource. Now let's trigger an OM kill. We'll allocate more memory than the limit allows and watch the kernel kill the process. First, let's create a Python script that will trigger OM. We'll use byte array, which is more memory efficient. Then we will run the script with a memory limit and see what will happen. The script kept allocating memory in chunks, and when it exceeded the limit, the kernel killed it immediately. And the cgroup is cleaned up after the process dies, so let's check dmesg instead. And we see the log about OOM. So what happened step by step? Python script allocated memory chunks by byte arrays, then each allocation succeeded until total reached the limit. On next allocation, memcgroup charge function saw that current plus new more than the limit. Kernel tried reclamation by memcgroup reclaim, and there is nothing to reclaim, no anonymous memory, no swap, and reclamation failed. And then memcgroup OOM function is triggered, and then OOM killer calculated scores and killed Python 3. But v2 adds a soft limit by memory.high, and let's demonstrate the difference. We will create modified script that allocates to 150 megabytes but stays under 150 megabytes hard limit. And then run with soft limit at 100 megabytes and hard limit at 150 megabytes. And we see that process runs fast until 100 megabytes and then slows down after 100 megabytes but doesn't die. When memory exceeds memory.high, kernel doesn't kill the process. Instead, it throttles allocations, makes them slower, and process can still allocate up to memory.max to 150 megabytes, but with a performance penalty. And unitized allocations taken longer after crossing memory.high. And this is proactive pressure management, not reactive killing. And the key difference is that without memory.high, fast allocations until 150 megabytes, then instant OM kill, but with memory.high, fast until 100 megabytes, throttled between 100 and 150 megabytes, and then OM kill at 150 megabytes. So, I think that's clear. And everything we have learned connects here. When you write a Kubernetes pod spec with the resource requests and limits, where does it go? And the answer is straight into cgroups. This demo uses Minikube, which works great on macOS. Important to understand that cgroups are a Linux kernel feature, so on macOS, Minikube runs inside a Linux VM using Docker desktop, and we will SSH into that VM to see the cgroups. First of all, we will verify that Minikube is running, and then create YAML manifest for each quality of service class. First one is guaranteed. It means that requests equals limits. Then is burstable. It means requests lower than limits. And next one is best effort. No requests or limits at all. Wait for pods to run. So let's check. In Minikube, all pods run on the single Minikube node. So now SSH into the Minikube VM to access the Linux kernel and cgroups. We're now inside the Linux VM that Minikube runs in. This VM has the actual Linux kernel with cgroups. On macOS, your host OS doesn't have cgroups, only Linux does. First verify cgroup version and we see that it's v2. The K indicator is type cgroup2. This confirms unified hierarchy. On v1 systems, you will see multiple mounts with the type cgroup. Let's look for cube pods. It might be under system slice in some configurations. Minikube typically uses the cgroup fs driver, not systemd, which creates sysfs cgroup cube pods. It's just simple directory, no .slice suffix. But some systems with a systemd cgroup driver use .slice suffix. So let's check what we have. Kubernetes creates 3 tiers based on quality of service class. First one is best effort. Its lowest priority equals to best effort quality of service pods. Next one is burstable. Its medium priority, and then pod UID, its highest priority. Its guaranteed pods direct under queue pods. And this separation enables differentiated eviction and resource allocation. The kernel enforces different resource limit for each tier. So let's inspect guaranteed pod. Back on our macOS terminal and then get pod UID. Now we'll check the cgroup settings for this guaranteed pod and we see CPU max. So the pod spec CPU 100 millicores directly translates to CPU.max in the cgroup. We will check memory limit and we see that it's 128 megabytes. So memory limit directly set from pod spec. This is the kernel enforcement point. So let's compare with the burstable pod. We will get burstable pod ID and check its cgroup path. The key difference between guaranteed and burstable, that guaranteed is when requests equal limits, then CPU.max cannot exceed 10,000. But burstable, it's when requests lower than limits and CPU max can burst up to limit. This allows burstable pods to use extra CPU when available, while guaranteed pods have strict caps. Next, we will get best effort pod UID and check its limits. And it should show max. That means no limit. Max means no limit, the pod can use all available CPU and memory, no CPU quota, it can use 100% of available CPU, no memory limit, can grow until node memory is full, and it gets killed first under pressure. To check OM scores, we need to find process PIDs. So the structure is pod cgroup to container cgroup and then to PIDs in cgroup.prods. So first of all we will get guaranteed pod UID, then find the pods cgroup directory and look inside. The cgroup structure is kubepod / pod UID / container ID. The container subdirectories are named with container IDs, those long hash strings, and the actual process PIDs are in the kernel-level cgroup.prods file. So, and we see that guaranteed pod have OM score adjustment minus 998. Then compare with the best effort, same approach, we see that it equals 1000, and there is OM priority hierarchy. When node runs out of memory, kernel OM killer plus kubelet eviction manager work together. Best effort pods killed or evicted first because we have OM score adjustment 1000. Then burstable pods exceeding requests, and then guaranteed pods only killed if they exceed limits, because we have OM score adjustment minus 998. And this is why quality of services classes matter. In production, critical services should be guaranteed. Background jobs can be best effort, and this prevent cascading failures. This entire chain from your YAML to kernel enforcement is visible and debuggable. When you have resource issues in production, don't stop at kubectl describe, SSH to the node, check the cgroup files, see what the kernel actually enforced. Let's bring this home with the production context. In production, P99 latency matters more than average. CPU throttling destroys P99. For user-facing APIs, we should to set CPU requests its guaranteed baseline and no limits. We should to allow bursting. But for batch jobs, we should to set limits to prevent runaway. Without limits, a compromised container can starve others. This is a security issue, not just operational. Always set memory limits. CPU are optional, but memory limits are mandatory. Every resource decision in Kubernetes uses cgroups, so you should understand quality of service classes, guaranteed for critical services, burstable for standard workloads, and best effort for batch or background jobs or something like this. Let's recap what we have learned. Cgroups are the kernel mechanism behind every container resource limit. When you set a memory limit in Docker or Kubernetes, you are writing to a cgroup control file. When a process gets killed, the kernel cgroup subsystem did it. And we explored two architectures: cgroup v1, per controller hierarchies. It's complex but still widespread on legacy systems. It has multiple trees and same process in different locations. cgroup v2 has unified hierarchy, single tree, clear delegation, and pressure stall information. That's the future. We saw the difference between proportional allocation, its CPU that shares and CPU weight, and hard limits, its CPU max and memory max. Shares are fair, limits are strict. We watched the kernel enforce limits in real time, throttling CPU, killing processes on memory exhaustion, checking pressure before failure, and we connected it to Kubernetes, quality of services, classes. They map directly to cgroup configurations and OM properties. Guaranteed burstable, best effort, it's all cgroup under the hood. And the key insight that when you debug resource issues in production, don't stop at kubectl describe. Go to the node, inspect the cgroup files, check throttling stats, read PSI metrics. That's where the truth lives. Those 3 commands will tell you more than any dashboard. In the next video, we are moving to networking. We'll explore how network namespaces work, how IP tables create service routing, and how Kubernetes networking plugins like Calico or Cilium interact with the kernel. But you now have the foundation. You understand how the kernel isolates with namespaces and how it limits with cgroups. Everything else builds on these 2 primitives.